Weight shift control 2, 3. Aerodynamics. Let's now explore the intricate dynamics of roll stability and moments in the realm of WSC aircraft. As described in the Pilot's Handbook of Aeronautical Knowledge, the amount of dihedral or anhedral in a WSC wing significantly influences its roll stability. This feature can be advantageous for training wings or high-speed wings designed for extended cross-country flights. However, achieving a delicate balance between roll stability and the agility required for swift turns, akin to a sports car, is a key consideration for most pilots. This equilibrium is attained through a combination of anhedral and other crucial wing design elements, including nose angle, twist, and airfoil shape from root to tip. A noteworthy aerodynamic characteristic of swept wings is the concept of effective dihedral, influenced by both the physical anhedral in the wing and the effective dihedral resulting from wing sweep. This intricate combination of features contributes to the overall stability and rolling moments of a specific wing design. In the design of WSC wings, actual dihedral or anhedral can be incorporated, and even wings with inboard anhedral may exhibit some dihedral due to flex in the outboard leading edges. The flex in the wings, especially during turns or with added weight, introduces a dynamic element, creating additional dihedral and enhancing roll stability. The roll stability of a WSC aircraft involves a collaborative effort between the pilot and the wing. The pilot, through control bar input and weight shifting, initiates a rolling moment about the wing or carriage hang point. Simultaneously, shifting weight to one side of the wing induces an aerodynamic change, warping the wing and altering lift on each side, similar to the roll control mechanism in airplanes. These combined rolling moments contribute to the WSC aircraft gracefully banking into a turn. While the wing is a primary factor in roll stability, the carriage design also plays a role. Carriage weight and the resultant center of gravity, CG, influence the overall roll moment. Carriage aerodynamics typically have a minimal impact on rolling moments. The collaboration between wing and carriage design, meticulously matched by manufacturers for compatibility, results in a harmonious balance between stability and agility. Turning our focus to yaw stability and moments, the inherent design of the WSC wing allows it to fly directly into the relative wind, minimizing the need for significant turning about the vertical axis. Unlike traditional airplanes that rely on a vertical tail for stability, the WSC aircraft achieves this through the unique combination of swept wing design, wing twist, and airfoil shape from root to tip. The subtle yaw correction showcases the increased wing area mitigating yawing motion. Yaw stability in WSC wings is generally well maintained, with any initial adverse yaw during roll initiation gradually corrected by the wing's design. The presence of vertical stabilizers or tip fins in some wing designs further enhances yaw stability, providing additional tools for designers to fine-tune the aircraft's performance. Carriage moments also contribute significantly to yaw stability. If the area in front of the CG is greater than the area behind the CG, the carriage can exert a yawing aerodynamic force, contributing to the WSC aircraft's ability to track directly into the wind. Wheel fins exemplify one method used to enhance carriage yaw stability. In summary, the WSC aircraft exhibits a remarkable ability to track directly into the relative wind, eliminating the need for a rudder to coordinate turns. The nuanced interactions between the wing, carriage, and aerodynamic forces result in an inherently stable yaw characteristic. Turning our attention to thrust moments, we explore the impact of thrust on pitch moments based on its placement relative to the CG. This visual illustrates the scenario where the propeller thrust below the CG generates a pitch-up moment upon application, leading to a decrease in speed. Conversely, reducing the throttle diminishes this moment, resulting in a nose-down pitch and an increase in speed. Now, let's delve into the realm of stalls, a crucial aspect of WSC aircraft dynamics. As the angle of attack, AOA, on the wing chord increases, the airfoil experiences separation, initiating the stall progression. The critical AOA marks the threshold where the wing is fully stalled, rendering it incapable of producing lift, irrespective of airspeed, flight attitude, or weight. The visual vividly illustrates the stall progression as the AOA intensifies. In the context of WSC wings, the unique geometry causes the nose to stall before the tips due to the substantially higher AOA at the root chord. This phenomenon resembles stalling with airplane canards, where the nose stalls first, and the main wing or tips for WSC aircraft continue to fly, preventing a complete wing stall. Even in scenarios of high pitch angles, a pilot can maintain control as the nose drops due to the stalled condition while the tips continue flying. It's essential to recognize that stall characteristics vary among wing designs. High-performance wings, with less twist for enhanced performance, may exhibit a more abrupt stall compared to training wings with additional twist. Moving on to the intriguing phenomenon of whipstall tuck-tumble, such occurrences may arise when a WSC aircraft operates beyond its limitations or encounters severe turbulence. If the wing attains an exceptionally high pitch attitude, causing the tips to stall, a whipstall ensues. In a WSC wing, a significant portion of the wing area is positioned behind the center of gravity, CG, resulting in a strong nose-down moment when the tips and aft wing experience high drag. This immediate nose-down motion initiates a rotational momentum, preventing the re-establishment of laminar airflow across the wing. The severity of a whipstall can lead to different phases. Phase 1. A minor whipstall results in a nose-down pitch attitude, but the positive stability raises the nose to resume normal flight. Phase 2. If the rotational movement induces a vertical dive, an aerodynamic dive recovery may raise the nose to restore normal flight conditions. Phase 3. The rotational momentum brings the nose past vertical, but recovery to a vertical dive and eventual return to normal flight is still possible. Phase 4. Severe rotational momentum can lead to a tumble, from which there is no recovery to normal flight, and structural damage becomes probable. Now, let's delve into the interplay of weight, load, and speed in the unique aerodynamics of weight shift control, WSC, aircraft. Much like airplanes, sailplanes, and powered parachutes, PPCs, increasing weight leads to increases in speed and descent rate. However, the WSC aircraft introduces a distinctive characteristic. Adding weight induces more twists in the wing as the outboard leading edges flex further. This increased twist, reducing lift at the tips, creates a nose-up effect, consequently lowering the trim speed. While adding weight can enhance speed, it simultaneously diminishes the trim speed due to the unique twist characteristics inherent in WSC aircraft. Manufacturers make, models exhibit varying effects based on their specific designs. As outlined in the Pilot's Handbook of Aeronautical Knowledge, stall speed rises with increasing weight or loading, prompting some manufacturers to specify particular carriage or wing hang point locations for different weights. Certain designs necessitate forward center of gravity, CG, locations for greater weights, ensuring that the trim speed remains well above the stall speed for the wing. In WSC aircraft, the forces during normal coordinated turns mirror those experienced by airplanes. Greater bank angles result in increased resultant loads. The flight operating strength of an aircraft is depicted on a velocity-gravity (VG) diagram, illustrating velocity versus g, loads or load factor. Each aircraft possesses its own VG diagram, valid at a specific weight and altitude, akin to the principles detailed in the Pilot's Handbook of Aeronautical Knowledge. Transitioning to basic propeller principles, WSC aircraft share similarities with conventional aircraft, albeit with some distinctions. There is no corkscrewing effect of the slipstream, and there is less P-factor since the carriage generally flies with the thrust line parallel to the relative wind. Torque reaction does, however, exert a noticeable effect on WSC aircraft. Left-hand turn tendencies, for right-turning propellers, are common, and various cart designs may incorporate adjustments to counteract this effect. Engine configurations, such as pointing the engine down and to the right, are not making any adjustment, contribute to the turning effect, managed through pilot input. It's essential to note that the direction of propeller rotation can vary, with two-stroke engine propellers often turning to the right, resembling conventional airplanes, while many four-stroke engine propellers turn to the left, resulting in a right-hand turn. Pilots are advised to consult the Pilot's Operating Handbook, PO, for specific aircraft torque characteristics. In summary, the basic principles of aerodynamics apply universally to all aircraft, but the distinctive design of the WSC wing and separate fuselage or carriage presents a simplified and efficient aircraft.